shown before, different civil times are occurring at the same instant all over the world. This would mean that a ship sailing east or west would have to be setting its clocks continuously, which would not be at all practical. For the convenience of navigators, the Earth has been divided into zones. All places within a zone keep the time of the central meridian of the zone, not their own local civil times. Time zones are based on the fact that there are 24 hours in a day, and the distance around the world is 360 degrees. Therefore, the circumference of the Earth has been divided into 24 bands, 15 degrees in width. These 15-degree bands are the zones. The central meridians of the various zones are those meridians, east or west, which are integral multiples of 15 degrees. These zones have been designated plus in west longitude and minus in east longitude, each zone being also named by a number, which is called the zone description, and is equal in value to the longitude of the central meridian of the zone, converted into hours. Each zone extends 7½ degrees east and west of the central meridian. For example, the longitude of San Francisco is about 122 degrees west. 122 divided by 15 gives us 8, with 2 degrees left over. This remainder is less than 7½ degrees from the 120th meridian, and therefore San Francisco is in zone plus 8. To obtain Greenwich Civil Time, then, we have only to add a plus zone description to, or subtract a minus zone description from, the zone time. Remember, zone time is the time kept in an area 7½ degrees on either side of the central meridian of the zone, and is the local civil time of that central meridian. If we project this zone time diagram on a Mercator projection of the world, we can show the relationship of zone time to the times at various positions on the Earth's surface. This zone time is similar to our standard time, such as Eastern Standard Time, Central Standard Time, etc. This system has been extended to the ocean areas of the world in this fashion. Watch the little ship as it sails eastward across the Pacific Ocean. Now it reaches the border of a new zone. See how the clock jumps ahead 1 hour. The clock face shows the time the ship is keeping as it steams along. Now our ship reverses course and steams westward. See, as it crosses this time zone border, its clock jumps backward 1 hour. So remember that zone time plus or minus zone description will give Greenwich Civil Time. Now let us consider the matter of a new day in relation to the date. As one day ends and another commences at midnight, or at the lower transit of the mean sun for any position on the Earth, it is evident that a new day is always commencing somewhere in the world. Consequently, there can be 2 different dates occurring in different parts of the world at the same instant of time. To help understand this matter of different dates occurring at the same time, let us consider the sun moving westward across the surface of the world, represented by this Mercator chart. The sun is now transiting the upper branch of the Greenwich Meridian, and therefore it is noon at any place on the Greenwich Meridian, and the date is the same all over the world. For example, let us assume that the date is the 24th. The gray area represents that portion of the world which is in the dark, and the heavy black line represents the meridian where a new day is beginning. That is to say, it is midnight at the black line, and a new date is occurring there. The eastern edge of the gray area represents morning, where the sun is rising, and the western edge represents evening, and the sun is setting. The figure in the box is the date for that particular meridian. As the sun moves to noon at New York, note that the sun has just transited the lower branch of the meridian of Singapore, and a new day has commenced there. Therefore, it has become the 25th at Singapore. When the sun reaches Honolulu, it is noon there, and a new day is beginning at Athens, Greece. The date at Athens is now the 25th. As the sun transits the 180th meridian, we know that the date at Greenwich has changed, as the 180th meridian is the lower branch of the Greenwich meridian, and therefore Greenwich will have the same date as places in east longitude, while places in west longitude will still be a day behind. When the sun reaches Manila, the date at Buenos Aires becomes the 25th. At Bombay noon, a new day starts at Denver, and it is the 25th. The sun continues on its way until it again reaches the upper branch of the Greenwich meridian, and it is now the 25th all around the world. To illustrate this same matter of dates in another way, let us view the Earth from the South Pole. Commencing with the sun on the Greenwich meridian, we know that it is noon there, and the date is the same all around the Earth. We will assume that the date is the 7th. As the sun moves around the Earth, it transits the lower branch of the meridian, capital M, small m. As it transits at small m, the date changes and a new day begins at capital M. If we allow the black area to indicate the positions where the date has changed to the 8th, we can see that the date of all places in east longitude becomes the 8th before Greenwich. As the sun transits the lower branch of the Greenwich meridian, it becomes the 8th at Greenwich, and all places in west longitude are behind Greenwich in date. As the sun again reaches Greenwich, we can see that the date is the 8th, and once more it is the same all around the world. In the matter of date, there is one important point which should be considered. This is the change of date as a ship crosses the international date line. Note that the date line follows the 180-degree meridian for the greater part of its length. Let us suppose that it is 1500 at Greenwich, and the date is August 8th. Observe that as we move eastward in longitude, the time becomes later and later, because the sun is farther past the local meridian. Until here, in 176 degrees east longitude, the zone time is 12 hours later than at Greenwich, and therefore it is 0300, and the date is August 9th. However, if we move westward from Greenwich, the time becomes earlier and earlier, until here the sun is on the local meridian, and it is noon. While here in 176 degrees west longitude, the time is 12 hours earlier than at Greenwich, and therefore it is 0300, and the date is August 8th, the same as at Greenwich. Thus we see that while the time of day here at 176 degrees east and at 176 degrees west are both 0300, the date here is August 8th, while here it is August 9th. This is always the situation adjacent to the international date line. West of the date line in zone -12, the date is 1 day later than it is east of the date line in zone plus 12. This change of date can be very well illustrated by the use of this ship. Observe as it steams eastward, the time is 0300 and the date is the 9th. As it crosses the line, the time of day remains the same, but the date becomes 1 day earlier, and it is 0300 on August 8th. Since data in the almanac are tabulated for Greenwich date as well as time, establishing the date at Greenwich is most important. Suppose that we assume our longitude to be 55 degrees west and the zone time 1900 on August 6th. As any place in longitude 55 degrees west is in zone plus 4, we add the zone time and the zone description, and the sum is Greenwich Civil Time. Since the total is less than 24 hours, we know the Greenwich date is the same as the local date. It can be seen that the sun has not transited the lower branches of either the local or Greenwich meridians since Greenwich noon. Therefore, the dates are the same. 3 hours pass by. Note that the sun has transited the lower branch of the Greenwich meridian, but it has not reached the lower branch of the local meridian. The zone time is now 2200, August 6th. To this, add zone description plus 4, and we find the sum is 26 hours. Therefore, at Greenwich, it is the next day, and the time is 0200, August 7th. The sun has transited the lower branch of Greenwich, but has not reached the lower branch of the local meridian. Therefore, the date at Greenwich is 1 day later than the local date. Let us now examine the problem for an observer in east longitude. Our longitude is 118 degrees east. The zone time is 2200, May 4th. Note that we are in zone minus 8, so therefore we subtract the zone description from the zone time. The result is the Greenwich Civil Time, 1400, and the date is still the 4th. 5 hours pass by. The zone time increases 5 hours and is now 0300. The local date is now May 5th. As our zone description is minus 8, it cannot be subtracted from the zone time of 3 hours, so we add 24 hours to the zone time and take away 1 day from the local date. Therefore, the Greenwich date must be earlier than the local date by 1 day, and the Greenwich Civil Time will equal 27 hours minus 8, or 1900, May 4th. Note on the diagram that the sun has transited the lower branch of the local meridian, but has not reached the lower branch of the Greenwich meridian. In this situation, the date at Greenwich is always 1 day earlier than the local date. In the foregoing discussion of zone and civil time, we have been considering the mean sun. However, the sun, which we see transiting our meridian, and the one on which our navigator takes his observations, is the apparent or true sun. The hour angle of the apparent sun is measured by apparent time. How to convert civil time to apparent time can be shown on this diagram. The white sun represents the true or apparent sun, and the gray sun represents the mean sun. As they apparently revolve about the world in the course of a year, note that the space between them varies, as first the true sun is ahead of the mean sun and then behind it. This angle is a measure of the time that the true sun is ahead of or behind the mean sun. This varying amount of time is called the equation of time and is tabulated in the Nautical Almanac against Greenwich Civil Time. As the note on the bottom of each page states, the equation of time is added to or subtracted from Greenwich Civil Time according to the sign which precedes it. As we can see, the Greenwich hour angles of the sun, which locate for us the positions of the true sun, are also tabulated against Greenwich Civil Time. The tabulated values are determined by taking the Greenwich Civil Time and to it applying the equation of time. This gives us the Greenwich Apparent Time, or the location of the true sun with reference to the lower branch of the Greenwich Meridian. As hour angles are measured to the westward from the upper branch of a meridian, we can see that it is necessary to add 12 hours to the Greenwich Apparent Time of the sun to obtain the Greenwich hour angle of the sun, if the sun is east of the meridian. If the sun is west of the meridian, we must subtract 12 hours to obtain the Greenwich hour angle. Now, the position of the sun has been located in units of time. As it is more convenient in solution of the astronomical triangle to use units of arc, degrees, minutes, and tenths of minute, the Greenwich hour angle is converted into arc, and this is the value in degrees which is found in the almanacs, tabulated with respect to Greenwich Civil Time. To convert Greenwich Civil Time to Greenwich Apparent Time, add or subtract the equation of time. To convert Greenwich Apparent Time to Greenwich hour angle of the true sun, add or subtract 12 hours. That is how Greenwich hour angles of the sun are determined and tabulated in the almanacs. A different method is used to determine the Greenwich hour angle of the stars. To illustrate this, we return to consideration of sidereal time, which is measured from the upper branch of a meridian westward to the hour circle through the March equinox. If we measure from the upper branch of the local meridian to the March equinox, the time is local sidereal time. If we measure from the upper branch of the Greenwich meridian to the March equinox, the time is Greenwich sidereal time. Note on the diagram that sidereal time is the same as the hour angle of the March equinox, as hour angles are also measured westward from the upper branch of a meridian. Due to this relationship, the Greenwich hour angle in units of arc can be tabulated instead of Greenwich sidereal time in units of time. This is the basis for one of our systems of tabulation of Greenwich hour angle in the almanacs. Therefore, the Greenwich hour angle of the March equinox plus the sidereal hour angle of a star gives the Greenwich hour angle of the star, which is required in navigation to determine one of the coordinates of the star, the local hour angle. Born in the vastness of space and measured by the perfect regularity of the rotation of the Earth upon its axis, time is the essence of celestial navigation.